The Turing tape of the Collatz conjecture. So if the conjecture is true, that the algorithm is a total Turing machine, which means it always halts. Furthermore, it always halts on 1. That is the conjecture. The 3x plus 1 function is a Turing machine. It meets the definition perfectly. It has inputs and outputs that determine which way a hypothetical tape moves, up or down or left to right. And this tape always ends at its beginning with 1. So I'm describing it a little bit naively, but that's good enough for me. So yeah, a Turing machine performs a series of atomic operations. Instead of thinking about sequences, one can think about this tape, and you can think about the input, the output, and the instruction about which direction the tape should move based on the difference between the input and the output. And it moves in relation to a control unit that is colloquially called a head. So we see the tape, and of course this is an infinite tape of which I am only showing the first few numbers, starting with 1. There's an input, there's an output, and there's an up or down direction which is given by negative number or positive number. And there is this concept of the head or control unit. And you can imagine the head reading the tape and then deciding which direction to go. So there's more information I'm showing on this tape than is needed by the head. The head only needs the input number because it knows the function of the algorithm. If I expand on part of the tape, we can now look at some input-output numbers and how they work. So input, let me get the laser pointer. Input 57, output 43. Input 43, output 65. Input 65, output 49. Input 49, output 37, and then we're off the tape. So that's the idea. And we are doing all this with 3 operations, A, B, or C, the letters that buy the numbers, as inputs and outputs. And you must consider every output number to be the input of the next atomic operation. So the 3 operations are A, B, and C. A is every second odd number, and B is every 4th odd number, and C is every 4th odd number. If we count up the numbers of B's and C's, it's equal to the number of A's. A is the operation that produces a difference that is positive, so 43 to 65, that's operation A. B is an operation that is negative, so 49 becomes 37, and operation C is also negative by a factor of 4, so that 53 becomes 13. And there's an interesting property that every output actually has 2 inputs, and this is not normally recognized in the even odd sequences, but is exposed by the odd sequences very clearly. Every output number that is not evenly divisible by 3 has 2 inputs, always C, and either A or B. So here we have a very small example, 67, and we see the inputs and outputs just as a regular sequence. We're not breaking them out separately. So input 67 is output 101, input 101 is output 25, input 25 is output 19. And we see the common differences. And I'll get back to that idea of common differences in more detail in the next slide. So we have a plus operation and a minus operation, a positive operation and a negative operation. And if we sum the pluses and minuses, we will get 1, always. For a sequence to end in 1, the common differences must add up to 1. It's that simple. This is the even-odd version of the same sequence, 67, and it actually shows, again, the differences, the common differences for the even-odd sequence, and the same rule applies. It must end in 1. And this is the graph, showing a sequence as one normally expects to see a sequence. So we are talking about common differences in the sense they are used in arithmetic. So the key to understanding arithmetic sequences is common differences. This is how you figure out the nth term of a sequence, linear, geometric, quadratic. And this works pretty damn nicely for Collatz sequences too, because the assumption is that it wouldn't work because the differences are random. Well, that's not altogether true. It's how you triangulate the differences. And if you look at the 3 operations individually, you actually can create nth term sequences formulas, and I have shown this in a previous presentation. So we can just call them common differences, the positive or negative change between sequential numbers. And if you add them together, the sum must be 1, as I stated. The sequence must end in 1, because if you add them together, the sum must be 1, and it doesn't matter what order you add them together. The sequence could be in some hypothetical different order. If the same numbers are present, you will get the same result. The sum must be 1. So for this reason, we don't even need to think about sequences as dynamical or anything like that. They're static sets that sum to 1. And state that if a loop were ever found, which it will not be, the common differences must sum to 0 by definition. So again, it would be a set of numbers that sum to 0. It wouldn't matter what order the numbers were in. There would be no beginning of the loop or end of the loop. It's just a sum of numbers. It's arithmetic. So also, we may suggest that the plus 1 in 3x plus 1, which you can think of as an offset, is the reason that all sequences end in 1. So hence, 0 is impossible except for the trivial loop of 1 itself, 1, 4, 2, 1. Now I've explained this in a lot more detail in at least one other presentation, that by looking at zero summation and equilibrium in 3x plus n functions for which n is greater than 3, one can find the counterexamples that show exactly why a complex loop cannot occur for 3x plus 1. Thank you.